All right, this lecture is all about the design of binary adders and subtractors. And subtractors. All right, so here's what we're trying to do. And bear with me, this lesson is going to involve a lot of drawing. All right, so what we want to do is design a 4-bit binary adder, which means it's going to have 8 total inputs, we'll label them A3, B3, A2, B2, A1, B1, A0, and B0. The idea here is that we've got A is a 4-bit number, and those bits are A3, A2, A1, and A0, and we're adding it to B, which is also a 4-bit number, B3, B2, B1, B0. And we're going to add them up, and we're going to get a sum, which also is 4 bits, S3, S2, S1, and S0. But wait, I can hear you ask, what about the 5th bit? If we add 2 4-bit binary numbers, we should get a 5-bit result. Remember that when we design our systems, we're locked into a set number of bits, right? If we have a 4-bit system, we're adding 4-bit numbers, our results have to be 4 bits, everything has to be the same number of bits. But there is still the option for a carry. We're going to label it as Carryout. That would be the 5th bit. And we're going to go ahead and put its output sort of off to the side. In a modern processor or microcontroller, there's like an extra register that exists to kind of store the misfit bits, such as Cout. And so our 4-bit adder here has also our 4 bits of output, S3, S2, S1, and S0. And let's see, that's all we need, right? So now it's time to go ahead and set about designing this adder. Now, our technique that we know so far, which is to develop a truth table and then use that truth table to derive a minterm expansion and then simplify that minterm expansion, is great and technically would work here, but it's not very feasible. We have 8 total inputs, which means that our truth table would have 256 rows. So that's not what we want to do. So we need to find a better, more efficient way to design this system. And we're going to take advantage of just kind of the basic structure of binary addition. So if we just look at an example of binary addition, something like this, 1, 0, 1, 1 plus 1, 0, 1, 1, 11 plus 11. And we add them all up. We have 1 plus 1 gets us 0 with a 1 in the carry. We carry to the next one. And in fact, we could even imagine a 0 in the carry of this first column. Now we have 1 plus 1 plus 1 gives us a 1 in the sum and a 1 in the carry out, which goes to the next column. 1 plus 0 is just 1. And we carry a 0 over. And then we have 0 plus 1 gives us a 0. And then we carry out that extra 1. So that's what we're going to do. We're going to focus on, or rather take advantage of the fact that each of these addition operations is the same, right? We're doing the exact same thing. We're adding 3-bit values, we're generating a sum, and then we're carrying over to the next bit. So that's what we're going to do. We're going to build one circuit that does this. We can build that circuit using our basic techniques, and we're going to make it, not duplicate it, but copy it 4 times and build a structure that's going to look kind of like this. We're going to have, let's draw a box. And let's draw another box. If I can hit the corners correctly, good. Box. What are you doing down there, box? Right there. So we'll call this guy just add 3, add 2, add 1, add 1, and add 0. And it's going to have the exact same structure as before. Add 3 is going to get A3 and B3, and it's going to produce S3. Add 2 is going to have A2 and B2 and produce S2. A1, or adder 1, has B1 and A1 and produces S1. And adder 0 has A0 and B0 and produces S0. So there we go. Now for the carries, just like we saw here, the carry out of one column goes to the next column. So that's what we'll do here. We'll have the carry out of A0 go to the carry in of A1, and then we'll repeat that process over and over. And then finally, the carry out of our last adder is going to become our official carry out. And we also get a carry in on the input side, and we don't really need it for addition, but it exists. We get it for free. And as you'll see, it does have some use cases. There's some reasons, some interesting computer science and computer engineering reasons why you would want to take advantage of that carry in. So now let's design what goes inside this adder, and we're going to use our basic techniques to do this. So if we have on the input side A, B, and C, that's carry in. I'm going to write it as C just because I'm lazy. And then on the output side, we'll have carry out and sum. Now we list out all of our inputs for A, B, and C. And there we go. And now we flesh out the right-hand side. Let me draw a line to demarcate these. All right. 0 plus 0 plus 0 gets us 0, 0. 0 plus 0 plus 1 gets us 0, 1. 0 plus 1 plus 0 gets us 0, 1. 0 plus 1 plus 1 gets us 1, 0. 1 plus 0 plus 0 gets us 0, 1. 1 plus 0 plus 1 gets us 1, 0. 1 plus 1 plus 0 gets us 1, 0. And 1 plus 1 plus 1 gets us 1, 1. There we go. Now, each of these inputs, or excuse me, each of these outputs is going to be its own expression. So let's go ahead and start with carry out. We'll say that carry out. First, let's list its midterm expansion, generalized midterm expansion. Remember that we sort of label the row numbers to find our midterms, 0, 1, 2, 3, 4, 5, 6, and 7. So, carry out is a sum of midterms 3, 5, 6, and 7. Right on. So, now let's go ahead and write it out as a Boolean expression. 3 is going to get us, what? A prime and B and C, or A and B prime and C, or A and B and C prime, or A, B, C. We can use the uniting theorem with ABC to reduce all three of these terms. So for example, we can start with the C term. That's going to give us A, B. The B term on the next guy over here, that's going to get us A, C. And then finally, the A term is going to get us BC, which means that our simplified result for carry out is equal to AB or AC or BC. Very similar to the consensus theorem, but not quite the same thing. So there's our result for carry out. Let's go ahead and do the sum. We've got that the sum, or S, is itself a sum of minterms. What do we have? 1, 2, 4, and 7. So draw those out, or draw out the full Boolean expression. 1 is going to be A prime, B prime, C, or 2 is going to be A prime, B, C prime. 4 is going to be A, B prime, C prime, and 7 is going to be A, B, C. Now this one is not quite as cut and dry as the other one, but we can do some creative stuff here. For these first two terms, let's go ahead and factor out the A prime. And that leaves us with B prime C, or B and C prime, or A. And we do the same thing. We're going to factor out the A on the other side. That's going to leave us with B prime C prime, or B and C. Now, if we look here, B prime and C, or B and C prime, is just B XOR C. So we've got A prime and B XOR C. Or, and if we look at this term, B prime and C prime, or B and C, remember that's the equivalence operation, or the inverse of the XOR operation. And that's what we're going to take advantage of. We're going to write it as B XOR C prime. There we go. Now, if we go ahead and look at this, we can see that we have an XOR gate again. We have A prime and B XOR C, or A and B XOR C prime. So if we say let X equals A and Y equals B XOR C, well, then we have A XOR B XOR C. And because of the associative property, we'll get rid of those parentheses, and we'll finally say that S is just equal to A XOR B XOR C. There's our design for our output. There we go. Now the only thing left to do is draw those logic diagrams. So let me really quick just jot everything down here real fast. We've got S already, which is a function of A, B, and C, and is equal to A XOR B XOR C. And we have C out, which is also a function of A, B, and C, which is equal to AB or AC or BC. And there we go. Now let's go ahead and draw it. We've got three inputs, A, B, and C. And let's say the first thing we've got is this XOR gate. Which takes from A, B, and C and produces our S. And then we have three 2-input AND gates. 1, 2, and 3 that are going to feed into a 3-input OR gate. Take another crack at that. There we go, much better. OR gate. It's really important for me to label those gates since I'm so terrible at drawing them. And that output is going to be C out, and it is going to take the first one from A and B, the next one from A and C, and then finally the last one from B and C. Let me go ahead and label these just to make it a little more clear. That's A, that's B, that's A, that's C, that's B, and that's C. So there we go. There's our logic diagram, as messy as it is. And that is our what we call a full adder. So there we go. We take that guy, and if we scroll all the way back up here, that is what goes inside each of these. Full adder. Wow, got sloppy there. Okay, so I'm going to go ahead and copy this because I'm going to use it again here in just a second down here at the bottom. Let's talk about subtraction. Now, we've talked about a number of different ways to perform subtraction, but the one we like the best, and we'll see why real quick. Let's see, subtraction. Specifically, we like that 2's complement subtraction. Remember that doing a minus b equals c is better if we do a plus negative b equals c. And to get that negative b, we use the 2's complement. And remember, the steps to get 2's complement are first invert. I'm just going to say invert b, and then say add 1. All right, so these are the things we need to do, and I'm going to go ahead and drop our adding circuit back in here. I'll get out of there. Let me try to move this back over where we can use it. There we go. So the first thing we need to do to get a 2's complement number is invert b. Now that's pretty easy because all we have to do is just invert the individual b inputs by adding NOT gates to each of the b inputs to the full adder. B2. B1, and B0. So there we go. That has the effect of inverting B. The last thing we need to do is add 1, and that's where this Cn comes into play, right? We have this ability to add a number, a 0 or a 1, to our adding circuit. And so if we just set Cn equal to 1, that has the effect of adding 1 to our circuit. And now, by adding inverters at the B inputs and putting a 1 on Cn to the adder, this is now a 4-bit binary subtractor. And there we go. So that is all for this lesson. Just to kind of recap, we talked about how to design a 4-bit binary adder. And really, the goal here was, one, to just have a little bit of fun, design a circuit that has real-world applications. These circuits are used in processors and microcontrollers all over the place. And illustrate how we can use our basic techniques of truth table, generalized minterm expansion, Boolean expressions, optimizing those Boolean expressions, drawing logic diagrams in order to get something real. So that's it for today. As always, if you have any questions, comments, or concerns, please let me know. And if not, I'll see you guys next time. Thank you.